of the problems that many people encounter when moving from primary to core is getting used to the visual differences between the two systems. And core can be pretty overwhelming at first. None of the most commonly used modules appear in the structure view with their names written on them. Like in primary, when you load up a separator, for example, it says separator on it. In core, you tend to just get a graphical image with inputs and outputs. And sometimes, like with the math modules, it's really obvious what they're for, and with some of the other ones, it can be pretty confusing at first. In this video, I'll go over several of the visual differences between core and primary and try to get you used to the different signal types that are available to us. Alright, so by right-clicking anywhere in the main area of a core cell, we can gain access to three menus: the built-in module menu, the expert macro menu, and the standard macro menu. And just like in primary, all of the macros are made up of built-in modules connected together. So we'll be focusing mainly on the built-in modules, and although they can be a little complex graphically at first, there's actually only about 30 of them, so there's not too much to remember. So despite the fact that event and audio signals work the same once they're inside core, there are still several different signal types for us to work with in core. So let's load up an add module and cover the first signal type, which is floating points and integers. By default, all of the math modules are going to accept floating point signals instead of integers. And you can change this in the function tab of these properties. In the signal type area, you can select integer, and you'll notice that the inputs and outputs of the module turn to little equal signs. So let's just quickly discuss what these are and how they work. Floating point signals are the same type of signal that you use in primary to pass around any piece of numerical data. So those are the same thing. And an integer is very similar to a floating point signal, and the difference is that it can only hold whole numbers as values. And if you try to give it anything else, it'll just take that number and it'll round it to the nearest whole number. So for example, you can feed a module with integer signal type a floating point value. And if you do, the floating point value will enter the input and just be rounded to the nearest whole number. And likewise, you can connect a integer signal to a module using the floating type signal. And the reason why you generally don't want to do that unless you have to is translating between the two types takes computational time, so it's just a waste of CPU if you don't need to do it. So the second signal type that we can use is called a boolean, and there are only 5 signals in core that use this signal type. They're all at the top of the flow menu here. And honestly, I pretty much only ever use the top 2. Very rarely are the other ones ever used for anything. So let's check out the compare and router modules. The compare module takes 2 values that are either floating point or integer as their inputs and outputs a single boolean value. And by default, they're set to be compare greater than. So for example, if A is greater than B, but you can also change this in the properties in the module parameters section of the function tab. So the only module that I ever use that accepts a boolean as an input is the router module. And this router module works almost identically to a primary distributor with 2 outputs. So what's going to happen here is if A is greater than B, then the Boolean coming out of the compare module will say true, and when A goes into the router, it will get routed to the top if A is greater than B, and it will get routed to the bottom if it is less than B. And you can process these two signals differently and use a merge module, which is also in the flow menu, to get the signals back into a single stream. So let's say, for example, if A is greater than B, we'll subtract 1 from A. And if A is less than B, then we'll add 1 to B. And then we can take both of the outputs from the add and subtract modules and run them into the same merge. And this is what is known in programming as an if-then statement or an if-then-else statement. So if A is greater than B, do one thing, else do something different. This is a very common structure that we're going to be using an awful lot of. And the last type of signal that I want to cover for this video is called a latch. And these are most commonly used with the read and write modules from the memory menu. Now, on their own, neither of these modules can do much of anything. The read module can store a value that can be read, but it has no way to write that value to store. And similarly, the write value can write a value to be stored, but there's no way to read out. So to use these two modules in conjunction with each other, you use the square inputs at the bottom, which are called latches, to connect them together. And now whenever you receive an input at the read module, it will read out whatever the last value written to the write module was. And to see how this works more fully, let's look at a macro in the expert macro menu under submenu memory. So this macro is also called a latch, and it basically functions exactly like a primary value module, in that you can write a value into the upper input, and whenever you receive a value at the lower or clock input, it will output the value written to the write module. And I'm not going to cover the read and write modules more in full right now because I'm going to devote a whole video to them next, so we'll just cover it there. Counter is a very basic building block that we'll be using in several projects further down the line. There's a counter at the heart of every oscillator. We're going to use them for envelopes, for delays, and probably for some other stuff as well. Alright, so let's get started. A counter requires a read module and a write module. And once we have them added, we can connect them together using their latch ports at the bottom. And if we decide that we want one of them to be an integer, you'll notice that the latches disconnect from each other, so both of these modules must be the same type, either float or integer, in order to be connected together. And we're going to take the output of the read module and use an integer add module to add 1 to the value. And you can easily create a constant value by right-clicking on a port and choosing the new quick constant command. And you can store the value in the write module. So every time we receive an input at the clock of the read module, we're going to take the value we have stored, which defaults to 0. It'll start at 0. And we'll take that value and add 1 to it for each clock that we receive. That new value is then stored in the write module so that the next time we get a clock at the read module, it will be equal to 1, and then the next clock will be equal to 2, and so on and so forth. And we can quickly modify this to be clocked by the sample rate clock by right-clicking and choosing the Connect to SRC option. And depending on what your sample rate is, you can see that mine is set to 44,100 in the upper right-hand corner here. That's how many times the read module will be read per second. So the value at our output should be increasing by 44,100 per second. And we can rename the output samples, and we can test this by reading the value using a numeric readout. So let's add that, and we'll set the audio core cell to be mono and the numeric readout to be always active. And you'll see our counter starts counting. We can make this a little more complicated by adding an option to restart the counter from 0. And we can do that by using another write module. And we're going to connect this one before the read module. And we can't do it because it's a float, so we have to switch it to an integer. And we're going to have this get fed by an input. Now we have to set this input to be an event input. And the reason for that is, if we tried to set it to an audio input, that value would write to the write module for every tick of the sample clock, because audio inputs to a core cell are sampled at every sample clock, whereas event inputs only arrive when an event actually shows up at the input. So let's name that input restart, and we're going to send it a value of 0 whenever we want to restart the counter. So I'm just going to use a value module that holds no value and set it to mono, and then we can right click on the trigger input and use the create control option to create a simple trigger button. And whenever we press this button, you'll see our counter restarts. Alright, so let's slightly modify our structure to output the number of seconds that have passed since the last restart value has arrived. And we want this to be able to give us fractions of seconds, so instead of using integers, we're going to use floating point read and write modules. And it'll be written to 0 whenever we get a restart event. And just like the other one, we'll read it out at every tick of the sample clock. And we'll write our final value to a write module. And the only way that this is really going to differ is in the value that we add to our number each time. And instead of adding 1 to it, we're going to add the amount of time that has passed since the last sample clock in seconds. So if our sample clock is set to 44,100, that means 1/44,100th of a second passes for each sample clock. So we can simply divide 1 over our sample rate and add that to our stored value every time. To access the sample rate, simply right-click and choose the Connect to SRR option. The SRR is different than the SRC in that SRR is going to be a constant value equal to the sample rate, 44,100, where SRC is always equal to 0. It's simply a clock that's moving at the sample rate. And we can check this code by duplicating our numeric value here and renaming it seconds and connecting it to our new output. In this video, we'll talk about how to make oscillators from scratch in Core. To begin with, we're going to create a building block called a phase accumulator. And what a phase accumulator is a counter that keeps track of which part of the oscillation cycle we are at currently. So to begin with, I'm going to use a read and write module to create a counter, just like I did in the previous tutorial. And just like before, we're going to read out our value at every sample rate clock, and we're going to add a number to it. And what number we're adding every time is dependent on the frequency of the oscillator, so I'm going to leave that part blank for now. And we need to add one more thing, which is what separates a phase accumulator from a normal counter, and that is that we want to keep our value within a certain range. So for an example, I'm just going to create a accumulator here that is always within the range of with a minimum value of -1 and a maximum value of 1. And in order to do this, I'm going to use a compare module and a router module. And like I said previously, pretty much you'll always want to use these two modules together. And I also mentioned previously that you can use the router and the compare in conjunction with a merge module to create something called an if-then statement. So in this particular instance, we're going to check if our signal is greater than 1, and if it is, then we're going to subtract 2 from it, and that way our value, anything greater than 1, subtract 2 will always be greater than -1, our minimum value. And if it's not greater than 1, then we're going to do nothing. So our value coming into the router module here is going to go out the bottom input if it's not greater than 1. And we can connect that bottom output directly into our merge module. And if it goes out the top output, that means our value is greater than 1, and we want to subtract 2 from it. So we can use a subtract module with a quick constant to do that very easily. And you can change the value of a quick constant in the properties in the function tab. So we'll merge those two values together and then send them to our write module. And this will ensure that we have a signal that's always between the values of -1 and 1, as long as the value that we're adding every time is greater than 0 or equal to 0. Alright, so now let's calculate the value that we're adding to our phase at every sample clock. And like I said, we'll need the frequency of the oscillator for that. And we need to get this information from primary, so I'll create a new input and name it frequency. We do, in the standard macro, under the convert menu section, have a macro called pitch to frequency, or P to F, that will translate from pitch to frequency for us. But this module is actually less precise than the one in primary. And it's precise enough that you probably would never notice the difference, but I like to use the primary one anyway, and that way if you're using any primary modules or oscillators along with your core ones, they'll all match up frequency-wise. Alright, so the next thing I'm going to do is divide our incoming frequency by our sample rate. And we're going to take the output of that value and we're going to multiply it by 2. So what this is going to give us is a number that when we add it together 44,100 times per second, as we will end up doing with my sample rate set to that value, will add up to twice of the frequency of our oscillator. And the reason why we want it to add up to twice the frequency of our oscillator is we are keeping our phase accumulator in a range from -1 to 1, so it's got a range of 2. So every time we want to complete one full oscillation, we need our phase accumulator to rise by a total value of 2. And the phase accumulator will keep, as we've programmed already, will keep that value within a range from -1 to 1. And every time we get over 1 and cycle back around, we've begun a new oscillation for our oscillator. And a phase accumulator itself is basically a ramp oscillator. And to show you what it looks like, I'm just going to create a simple scope out of an XY module. And this is just a simple scope that I like to use to show one full oscillation of an oscillator whenever I'm designing anything in Core. And what we do is we make a ramp oscillator with an amplitude of 2, and we subtract 1 from the output. Now, ramp oscillators are a strange kind of oscillator that instead of ranging from the negative amplitude to the positive amplitude, ranged from 0 to the amplitude. So it outputs a value from 0 to 2. We subtract 1 from it, we get a value from -1 to 1. And we'll use that to control the x of our XY module. And we'll control both of the oscillator we just created and the ramp oscillator with a MIDI pitch translated into frequency. And we just need to set the scope itself, or the XY itself, to being in scope mode. And, well, it's drawing 4 wavelengths at once right now. Well, we need to change the range from -1 to 1 on both the X and the Ys. Alright. So, you can see it's just basically a simple ramp oscillator or inverted sawtooth that our phase accumulator looks like. And since our whole structure is polyphonic right now, it's drawing 4 waveforms, so it kind of looks a little ugly, but here you have our basic phase accumulator. So the last thing I want to do is make our phase accumulator a little more versatile. Right now, it always ranges from -1 to 1. And what I would like to do is make it so that we can declare a constant value called n and have the phase accumulator range from -n to +n. So let's look at how to do that. So first, let's delete this value 1 in the compare module and replace it with a quick bus. You can create a quick bus by right-clicking on any input or output and choosing the Connect to New Quick Bus command. And what a quick bus is it's basically a way of making connections without using wires. So we can connect this same value n to any other input and it'll all connect back to the same value, and then we'll declare one value that's equal to n at the end, as I'll show you. So we already replaced our value 1 with the value n, and now we're going to replace all of our instances of the value 2 with the value 2n. So I'm going to take n, multiply it by 2 using a multiply module and the quick bus and a quick constant, and we're going to create a new quick bus by clicking on the output and calling that 2n. Now you can right-click on the inputs and use the Connect to Quick Bus option to connect to the value 2n at both of our instances of the value 2. And the last thing we need to do is declare our value n so that Reactor knows what it is. So I'm just going to create a constant module, connect it to the quick bus n, and it's going to be 1 by default. And right now it's drawing the 4 oscillators again. What's happening is we're in polyphonic mode and it's drawing 4 things at once. So I'll just reset our clock and get them all back in phase. And to finish up, I'm just going to change the range of our phase accumulator so it goes from -pi to pi, and we'll use that value to control a SINE module, which you can find in the expert macro under the math and trig menus We have a whole bunch of functions here. So we can choose the SINE function and use the phase accumulator to control it. And this will be a simple sine oscillator. And once again, we're drawing 4 of them. I'm just going to set this whole instrument to be mono, so we can stop looking at that. And there's our sine oscillator. So the first thing we're going to do is separate out the part of our code that makes up the phase accumulator, which is everything besides the sine function in this core cell, and copy it using the control copy function. And let's add a new macro by hitting enter and typing in macro just like you would in primary, and jump inside the macro and paste our phase accumulator code. And I copied everything but the output, so I'll just add a new one and connect it to the phase. We can name it pH, and can name our whole macro. And I just like to keep everything as neatly organized as possible. It really does help out later on when you are not quite sure exactly what each piece of code does at a glance. Macros with descriptive names can be very helpful. You can just say, oh, this is the phase accumulator. I know what it does. I don't really need to worry about what the code looks like, and it just makes everything way smoother in the future. So let's take the old phase accumulator code and delete it, and insert the macro we just made in its place. And notice how our core cell structure has gotten a little spread out here. It's all this extra room, and we can shrink it back down to size again by right-clicking anywhere on empty space and choosing the compact board function. Okay, so the next thing I want to do is to add an input for our phase accumulator macro for the value n. Instead of using a constant inside the macro itself, I want the user to be able to supply this value. And that's because different oscillator algorithms require different values of n. So this just makes it easier for programming later on in the future without having to muck about inside this macro. So I'll just create a new input, name it n, and then connect it to the quick bus n. And you'll note that when we do that, the old n value disappears. And that's because, you can only have one value supplying that quick bus at any given point in time. So we can delete the pi value that we had previously declared. And the last thing I want to mention is this cool little feature that core inputs have, where you can declare a default value, and if that input is not connected to anything in the larger structure, then the default value will be used. So I'm just going to declare a default value for n of pi because it's the most commonly used value for a phase accumulator to use. And when we jump back to the larger structure, since n is not connected to anything, it's simply going to default to pi, and we'll have the same values coming out of the phase accumulator as we did before. Next, let's add a gate sync function to our phase accumulator. And what the gate sync function is going to do is simply restart the phase accumulator from 0 whenever we receive a positive event at the gate input. So I'm going to make a new input in the core cell and in our phase accumulator macro. And you want to make sure that the input to the core cell itself is marked as an event input and not an audio input, because an audio input will give you problems if the gate is greater than 0 and it's an audio value. It'll get sampled at every sample clock, and it'll be constantly restarting the oscillator whenever the gate is greater than 0. And if you have it set to an event, that will only trigger one time on a new gate event. So whenever we have a gate event greater than 0, we want to set our phase to equal to 0. So I'm going to create a write module to write that value of 0. And we're going to use a latch to trigger our function. So whenever we get an input to the bottom port of our latch module, it's going to send the value at the top input to the output. And if we leave the top input disconnected, it'll just default to a value of 0. And we only want this to happen when we know that the gate is greater than 0. So I'm going to use the combination of the compare and router modules to compare the gate to 0. And if it's greater than 0, we'll trigger our latch module. So the gate will go into the upper input of the compare and the lower input of the router, and we'll use the upper output of the router to trigger our latch module. And creating this gate sync input can be useful for a couple things. It's especially useful for testing waveforms, because we'll be able to look at the same exact waveform every time we trigger a gate. It won't start at some random part of the cycle. And another useful thing is for when we get into frequency modulation and the like later on, it's useful because it ensures that our waveforms are always going to be the same and we'll always get the same sound out of them. And here's our sine wave centered around the 0 and synced to the new gate. Alright, so next let's add frequency modulation to our phase accumulator. So we'll start by adding an input to the macro itself called FM, and the value at that input can be added to our frequency. And just like with the primary FM modules, the FM value can be very large or very small. It can be plus or minus thousands. So when we add it to the frequency, we're not guaranteed to end up with a positive number. And what that can mean is that sometimes we'll end up adding negative values to our phase accumulator. And this isn't a big problem, but we're not currently set up to deal with this. And, you know, like I've been saying, we want to keep the phase output equal to a value between negative n and positive n. And we're not checking at the moment to see if we ever go below negative n. And the reason for that is because we've always been adding positive values up to now. But now that the values that we're adding can go negative, we need to add a second if-then-else module to our structure. So let's just duplicate our first one and we can change a few values around. So we're going to check if the input to our if-then statement is less than negative n. So we'll replace the n with a negative n value. And next you can change the compare module's function in the function tab of the properties under the module parameters section, and you can choose to compare whether A is greater than B, less than B, equal to B, etc. So now we're checking if our input to the top port is less than negative n. And if it is, instead of subtracting 2n, we want to add 2n. So we'll delete the subtract module and put in a new add module. Alright, and this whole structure that we just created can go directly after our last if-then-else statement. So let's make ourselves some room, and it can receive its inputs from the merge module we made last time. And it'll output to the same outputs. Alright, so finally all we need to do is add an FM input to our core cell itself, And we'll keep the FM input as an audio signal, which it needs to be if we're going to get audio speed FM, of course. Alright, in the next video we'll test this oscillator a little bit, and I'll show you how to add some phase modulation as well. So the oscillator we've been designing so far is very similar to a primary sine sync oscillator. And I like to test my core work against existing primary cells when possible, just to get an idea that things are working properly. So I'm going to make a quick scope using the sine sync oscillator from primary, and we're going to create a little bit of frequency modulation to check out that these two oscillators will behave identically to the same inputs. And I'm going to use another sine sync module for our FM signal. So that's going to get the same gate signal as our other two oscillators. Oops. But we want it to have its own pitch control, and I'm going to give it its own amplitude knob as well. And the amplitude knob is going to control the depth of the FM, and the pitch control is going to control the speed of the FM. This is just a very ugly rudimentary system, but it'll give us a good idea of whether or not these two oscillators are going to react the same. And since we are restarting all three of the oscillators with a new gate press, whenever we receive a new MIDI note, the outputs of our two oscillators should be identical. And as we see, when I press a note, they line up precisely. And so that's the reason why we added the gate sync function to our oscillators. If we remove the gate input, you'll note every time we press a note, the shape of the oscillator is changing. And that's not necessarily a bad thing. You might want to have it change every time, but just for consistency's sake, I like to at least have the option of restarting the oscillator on a new MIDI note. So now that we've verified that our frequency modulation system is working properly, I'd like to add phase modulation to our oscillator. And while phase modulation is less well known than frequency modulation, as a name anyway, a lot of the things that you think of as being frequency modulation, such as the Yamaha DX7, are actually implemented using a phase modulation structure. And so what phase modulation is we're going to take the output of the phase accumulator that we've created and modulate it with another audio signal. So I'll create a new audio input for our phase modulation signal, and a new macro where we'll do all of the work. So we'll take the phase as one input, and we're actually going to need the value n for another input. So I'll output the value n from our phase accumulator module, and we can create a new input for n. Let's copy the one that we have existing already and paste that into our newer macro. And the output of this macro is going to control the input to our sine function. It's going to become our new phase, so we can connect that to our larger structure and rename the macro to phase mod. And finally, let's add an input for our modulating signal and name our inputs. Alright, so we're going to assume that the phase mod signal is going to be in the typical digital audio range from -1 to 1. And our phase, as we know, is going to range from -n to +n. So in order to make sure that our phase mod signal is in the range of n, we're going to multiply the phase mod by n. And this way, for example, if n is equal to pi and our incoming digital audio is from -1 to 1, then we'll get a phase mod signal that ranges from negative pi to pi, and that way will affect the whole range of the phase. Or basically, we're just translating our phase mod signal to have the same range as our phase accumulator. And once these values are normalized like that, we can simply add them together, and this will give us our new phase. Now, the only problem we have is that our new phase might no longer be in the range from negative n to n because we've just added this new value to it. So what we're going to do is use the same function that we used in our phase accumulator to keep our signal in the range from negative n to n. So I'm going to copy these two if-then statements and paste them into their own macro. And this macro we can name wrap, and it'll just wrap the value, the incoming value, into a range from negative n to positive n. So just connect our copy-pasted modules to the inputs and outputs, and we need to supply the value n because we didn't copy that. So I'll make a new input with a quick bus. We'll just connect it to the existing n quick bus, and we also need to make the 2n quick bus, so we'll just multiply it by 2 and connect the output of that to 2n. And this is our new wrap macro. And I like to do this as much as possible, take any functionality that's going to be repeated or reused and turn it into its own macro, and that way when you go back to look at your code later on, it just makes a lot more sense. So let's delete this old code and fit our new macro in place. It just makes the whole function look a lot cleaner and a lot easier to tell what's going on. Alright, so now we can copy this wrap macro and paste it into our phase mod macro. And we'll take the value after it's been modulated and make sure we wrap it back around into the range that we want. And that'll be our phase accumulation setup. And finally, let's add an amplitude input. This is pretty much the easiest of all to implement. We can simply make our audio rate input and multiply that input by the output of the SINE function or whatever function you're using to shape the phase into an oscillator. And that's it. In this video, we're going to set aside the oscillators for a bit and talk about a built-in module type called arrays, which you can find in the memory menu. And we'll be using this array to create a simple delay macro. But first, let's talk about how they work. Notice that the output port for the array is very similar to the latch inputs and outputs used by the read and write modules, but it's slightly different. It has this little line at the end here that denotes it as an array and not a single value. So an array can hold many different values at once, and it can be used to create a similar functionality to the primary event and audio tables. There's only two types of modules that will accept the array latches as inputs. There's the index module and the size module. And we'll talk about what those do. The size module is simple. You simply connect it to the array and it outputs the number of values that that array holds. And you can set the number of elements an array has in the function tab of the properties. So if I set the number of values to 1024, then the output of the size module will be 1024. The index modules are used in conjunction with the read and write modules. So they have the array latch as an input and a normal latch as an output. And by supplying an index value at the integer input, we can select a single element from the array and read it and write it using the read and write modules. And before we move on, just a quick word about index values. If you have an array with 1024 elements, then the index values will range from 0 to 1023. And so since you're using 0 as the index for the first value, the maximum value will be 1 less than the size of the array. So if I wanted to read the maximum array value, I would read value number 1023. And that's just a computer programming convention that's been around for a long time. So you're probably thinking that this whole system of using indexes and reads and writes is a little strange and unintuitive compared to the tables that we have access to in primary, but accessing the values individually like this, or being able to add as many read and write modules to an array as we want, kind of gives us a lot more freedom to manipulate the values and sort through them and do all sorts of stuff that would be really complicated in primary, and hopefully we'll get around to doing some of that a little bit later on. And there are some built-in modules in the expert macro section under the memory menu called read and write for arrays. And these will already just have the index built in, and they'll just allow you to declare which index and read and write values depending on which module you're using. So I'll pretty much always use these instead of building my own macros using the indexes, because they'll end up doing the same thing and it's just faster and easier. Alright, so that's the basics of arrays. Now let's talk about how we can use one to build a simple delay. So what we're going to want to do, first of all, is to write all of our incoming audio to an array. And once we have the audio stored, we can play it back, delayed from its original time. So we're going to use a counter to control the index of the array that we're writing to, and we're going to count up to the maximum value of our array and then start again at 0, and the length of our array will be the maximum delay time. So let's say we want to be able to store up to 1 second of audio and have a maximum delay of 1 second for our delay. With a sample rate of 44,100, that means we'll need to be able to store 44,100 values in our array. So we can set our size, our array size, in the function tab of the properties. And next we can take an audio input and store the values from that input into the array. And any value that gets sent to one of these write macros will be written to the current index. So the last thing we need to do is create our counter that will increase the index by 1 for every sample and wrap back around to 0 when it goes over the maximum index size of the array. So this counter is going to store an integer, since the index of an array is always an integer. So we'll create the 2 read and write modules and read out the index for every sample tick, and then we'll add 1 to the value and test it to see if it's larger than our maximum value, and if it is, we will start it back at 0. So index plus 1, and we can get our maximum value out of the size module down here. And we'll create an if-then-else statement to keep our index in range. And hopefully these are becoming pretty familiar to you at this point in time. So again, our maximum value is n minus 1. So we'll compare our new index to n and see if it's greater than or equal to the maximum value, and if it is, then we'll subtract n. If not, then we'll just pass it through. So this is almost identical to the one that we built for our oscillator in the previous videos. And as we build more and more things in Core, you'll notice that there's really, as I mentioned, there's only like 30 modules that we can use that make up everything inside Core. And there's really only a few different types of operations that we need to do. So, we have read and write modules and arrays to store data and read it back. And we have math to manipulate that data. And we have our routers and compare modules to create if-then statements. And those are, right there, most of the elements of traditional computer programming. And the one thing that we're missing is iteration, which unfortunately we need to use primary for. We can use the iteration module for that. And we'll get into some uses for that in some later tutorials down the line. And once we're done building this if-then-else statement, we're going to need to start building a way to read out the values that we're storing in our array. So in order to create a delay, how this is going to work is we're going to subtract a value from our index to read back. So for example, if we're writing to our array and we're traveling through our array going up by one value, one index every sample point, then if we subtract 100 from the index, then we'll play back the sound that was coming in 100 samples ago, which turns out to be a few milliseconds. So this works just fine, and the only thing we'll need to do beyond that is make sure that once we've subtracted, we haven't gone below 0, because there's no negative index for our array. So if we go below 0, we need to just add n to the value, and that'll wrap us back around to being within range. Alright, so we could just have delay be a value between 0 and 44,100 and subtract that from the index. But it's easier to have the delay just be a value between 0 and 1, and then we'll multiply it by n. And we'll translate the output to be an integer by just declaring a integer quick bus. Alright, so once we've subtracted, we can do our if-then statement that I was talking about before. And I just like to load the router, the compare, and the merge module all at once to save some time. And we'll check our value, and if it goes less than 0, we will add n to the output. Otherwise, we do nothing and send it straight to the merge module. And once we finish this if-then-else statement, we can use it to control the index of our read module, and we'll be pretty much done. I'll just spend a quick moment setting this all up in primary so we can get some sound out of it and do a quick sound test to make sure that everything's working all right. This is a really basic delay at this point in time, so we're not going to try to do anything too interesting with it, but just like to verify that things work as we're going along so that we don't end up having to go back and do everything all over again later. Alright, so inside primary, we're going to make this whole thing mono so we can delete the voice combiners. And delays are kind of pointless if you're not mixing them with the original signal. You can't really even tell what's happening. So I'm just going to use a crossfader to give us a mix between our original signal and the delayed signal. We can connect it directly to the outputs and use the create control command to create a crossfader knob and a delay time knob. And we're ready to do some testing. Oh, and make sure you connect the audio core cell as well, of course. Alright, and again, this is not exactly a high quality delay by any means, but it is a good way to illustrate how to use arrays and how to read and write from them. In this video, I'll show you how to make an optional clock in Core, and I'll be using the oscillator that we've been working on as an example. An optional clock is a method that we can use to turn off parts of a core cell that we are not currently using. And in that way, it has a similar function to the primary switch module. However, I find the core method to be a little more useful in the long run because we can switch things while audio is playing through them, which if you try to do in primary will cause an audio click. And we can do this without causing initialization errors, which primary switches also will do pretty regularly. Alright, so let's get started. First, I'm just moving all the contents of the core cell into their own macro, and we can hook it up to the inputs and outputs of the core cell. And when we're done, we can name it something like SINE oscillator or whatever. And I'm going to create an optional clock that makes the oscillator run only when the amplitude is greater than 0. And if the amplitude is equal to 0, we want to do nothing. So to achieve this, I'm going to use to start a compare and router module. And this is basically our if-then statement where we're going to ask, is amplitude greater than 0? And if it is, then we can proceed as we normally would. And that will be out the top output. And the bottom output we can simply have nothing coming out of, because if the amplitude's not greater than 0, then we're going to end up doing nothing. And we're going to connect a sample rate clock to the input of the router. And this sample rate clock will be routed to the top input whenever the amplitude is greater than 0. So let's create a new quick bus from there and name it clock. Now this clock value is going to read any signal that's coming into our macro that is audio rate. So we have 3 audio rate signals coming into our macro: the frequency modulation, the phase modulation, and the amplitude itself. And as I've mentioned previously, all signals that are audio rate inputs to a core cell are being sampled 44,100 times a second. So even if you have an event signal in primary connected to this audio input in core, the core cell is going to sample that event 44,100 times a second and create an event going into core. So what we're going to do is interrupt all of these signals that are coming in at audio rate and store them in latch macros. And we'll only read out the value stored in our latches if the clock is on. And this method will stop these audio signals from triggering any calculations downstream from them in the core structure. And the reason for this is that core modules function differently than primary modules. So for example, if you have a multiplication module in primary running at audio rate, regardless of whether you're using that signal or not, or whether the signal is changing or not, you're going to end up calculating that multiply module at every tick of the sample rate. So for me, 44,100 times a second. And in primary, a multiplication module will only be calculated when it receives an input at either the top or bottom input. So if it doesn't receive any value, then the multiplication actually doesn't get calculated, and that'll save us some CPU. So we're almost done, and the last thing we want to do is replace any instances where we're using the sample rate clock in our structure with this new quick bus clock that we've created. So in the oscillator, there's only one instance of the sample rate clock being used, and it's inside the phase accumulator. So I'll just add an input to the phase accumulator and route the clock to the input that is currently being used by the sample rate clock, and then we'll route it from our quick bus in this macro to the phase accumulator like so. Alright. And so finally, let's hook our oscillator up to a envelope and let's try to get some CPU savings here. So I'm just going to use a very simple AR envelope with an attack and release time of 0. And this is actually not going to do anything for our CPU at all. And if we go into the structure, we can see the reason why. So amplitude's minimum value when it gets released actually drops to some very small number, but it's still greater than 0. So our greater than 0 calculation is still ringing true. So I'm going to create a constant on the bottom of this, and I'm going to set it to something just barely above 0. So when the amplitude of the oscillator is very low, it turns off. And you can see the pretty substantial CPU savings that we'll get out of turning this oscillator off when we're not using it. Okay, so this method, of course, requires a little bit of overhead when the oscillator is running. It's slightly less efficient because we have this compare router module to do that we didn't have to do before. But if you have any elements in your reactor work that are taking up a lot of CPU that aren't necessarily always being used, this is a great way to conserve some CPU for your ensemble. Routers are the source of a lot of confusion for people who are just beginning in core, and I think the reason for that is that they don't really bear a whole lot of resemblance to their primary counterparts. So in this video, I'm going to show how we can use routers to create something akin to the 1-to-M router in primary and the distributors from primary. And later on, I'll show how we can kind of invert these structures to create something similar to the selector scanner module. So to begin, let's create a new macro, and I'll give it 2 inputs. And the first one's going to be named position, and we can just name the second one in or whatever. And we're going to set the position to be an integer. And next, let's load up a compare and router module pair and connect them together. And we want to set the compare to be an integer. There we go. And we're going to use the equals operator on it. And so we're going to test our input, our position input against this compare module, and then route our input through the router. And if it's equal to 0, then we can send it out the top input. And the kind of basic way to make a 1-to-m router out of this is just to duplicate that very simple structure for each output that we want to use. And so this is kind of how people will often do things instinctively, and it'll work, but the problem is it's just horribly inefficient. And so let's just delete most of it and I'll talk about why. So the way that these routers work is that the compare module is never actually calculated until we receive a value at the input of the router. And when it does, it checks to see what the compare value is equal to before routing the signal. So the way we just had things set up, we were connecting the input directly to all 4 router modules, which meant that all 4 compare values had to be calculated every time we received an input. So let's look at a slightly better method, and then I'll show you the best method for doing this. So we can duplicate our original structure here, and instead of routing the input directly into the router, we're only going to send a signal to this router if we already know that the position is not equal to 0. And as we extend this structure, we can achieve better efficiency as long as the value of position is not equal to the last possible routing value. So as long as position is less than 3, we'll save some CPU here. So this structure will work all right, but as I was just mentioning, it's going to get less and less efficient the higher the value of position gets. And that's just kind of an undesirable trait. We want something that's going to take up the same amount of CPU no matter what. And so let's look at a way to do that. And this structure we're going to build, we're going to minimize the number of router modules that have to be calculated for a router of a given size. So I'll build a tree router, which is a type of router that has a number of outputs equal to a power of 2. So we'll have 4, 8, 16, or 32 outputs, and depending on what the power of 2 is, that's the maximum number of compare router modules that we'll need to calculate for any given value. So I'm going to build a router with 8 outputs, and 8 is 2 to the 3rd power, so we'll never have to calculate more than 3 router compare module pairs. And just like in primary, you can hit enter and you get a list of all the most recently added modules, and you can select one from it, and it's just a really quick way to add some modules to your structure. Alright, so the compare modules that we're going to use for this structure are going to use a greater than or equal to operator, so we can select that in the properties. And we'll give our first one, we'll see if the position is greater than or equal to 4. And like I said, we'll have 8 outputs, so this is basically going to split our signals in half. Anything where the position is greater than 4, so it'll be the values 4, 5, 6, or 7 will go out the top, and anything where the position is less than 4, 0 through 3, then will go out the bottom. And next we're just going to split the signal in half again. So if we get something out the bottom input here, we know that we have a value from 0 to 3. So we can check to see if it's greater than or equal to 2. And if it is, then we know that the position is either 2 or 3. And if it's not, we know that the position is either 0 or 1. So we're constantly just taking the values and splitting them in half. So our upper structure is going to get a position of 6 for this iteration. And finally, we'll make our third ply here. And we'll check to see if the position is greater than or equal to 1. So the one above that will be 3, and then we'll make, to test to see, 5 and 7 as well. And those will go on the top half of the structure, of course, if we initially decided that the position was greater than 4. So this structure, you might have to build it yourself and just kind of look at it closely in order to really understand what's going on here. It took me a while to figure out the first time I built one, but it really does make a lot of sense. And if you look now at the signal flow from the input to any one of the outputs, once I add them, you'll see that we can never go through more than 3 router modules for any value of the position input. So I'll provide examples of a tree router with 4, 8, and 16 outputs with the included files with these videos. And next time I'll show how we can take one of these and turn it into something more similar to one of the selector modules from primary. Alright, in the previous video I showed how we could make a structure in Core that has a similar functionality to the router 1 to M module in primary, or the primary distributor panner module. And I'll show how we can do a simple edit of that macro to create another router type in Core that is similar to the primary selector scanner or M-to-1 macro modules. So I'm going to create a new macro with a position input that is an integer like before. And we're going to give it 8 inputs for audio signals to choose from. And this is just by way of example, and I'll include several more sizes in the ensembles included with this video series. So we're going to run each audio input into a latch macro, which, if you'll recall, is very similar to the primary value module. So any value that we store in the top input is going to stay there until we receive a clock at the bottom input. Alright, so I'm just going to name these inputs from 0 to 7. And the idea is that we'll trigger one of these modules' clocks at every tick of the sampling rate clock. And whichever one comes out, we're just going to merge all of the values together. So this merge value module will only receive one value at each sample clock. And this is kind of cool because we get to use a merge module with a audio signal, which we would not be able to do in primary. So we'll just merge all those values out and send them to the output. And the last thing we need to do is to figure out which one of these latch macros we want to clock whenever, depending on what the position is. And we can simply use our already designed tree router for this purpose. And it's going to receive the same position as our entire macro. And we can simply connect each output from our tree router to the corresponding latch clock. So output 0 is going to go to the latch that is storing the input of signal 0, and so on and so forth, all the way up to 7. And I'm just going to rearrange the outputs of our tree structure here so that everything looks a little cleaner in our main structure. And this way we'll have the same convention for starting with 0 at the top and counting down like primary routers do. Alright. So this should just look a little better in our larger structure. And the last thing we need to do is to supply our tree router with an input. And I'm just going to use a sample rate clock here. So for every tick of the sample rate clock, we'll check what the position is, and then we will read out the corresponding value from the latch that it's been stored in. And again, I'll have a few different sizes of these types of routers saved with the ensembles for this tutorial series. In this video, I'll show you how to make a basic ADSR envelope in Core. And this project will tie together several of the things that we've been working on so far. We'll be using a counter to time how long the envelope has been either on or off for. We're going to use optional clocking, so we'll get a closer look at that, see how it works, and we'll be building a somewhat sophisticated router in order to control our optional clock signal. So to start out on some familiar territory, I'm just going to build a simple counter, and this counter is going to reset at 0 every time we get a gate signal, and we'll be counting time in seconds. So basically, by resetting with each gate input, we're starting over at 0 whenever the gate turns on or whenever the gate turns off. And so we'll be either counting time for the attack decay period of the envelope, or we'll be counting time for the release period, depending on whether the gate is on or off. So at every sample clock, we're going to read the value that we have stored, and I'm going to send it directly out. And this way, when we set the counter to be 0, that's going to happen in between audio ticks. And when the next sample clock arrives, we'll send the value of 0 to the output of our macro. And then we'll add a small number to that, which is going to be 1 over the sample rate. So this is going to be 1 over 44,100. And we're going to add it to 0, 44,100 times a second. So over 1 second, it's going to increase by a value of 1. So this is just counting our time in seconds for us. And our envelope cell is going to receive times for the attack and decay and release. And we'll use the timer that we've just created to decide which part of the envelope is currently active. So we're going to use a router to do that, or a series of routers. And first we're going to check to see if the gate is on or off. So if the gate is on, then we could be at the attack, the decay, or the sustain period. And if it's off, we're definitely in the release period. So that's the first thing we can check. And if the gate's not greater than 0, then we can create a clock called the release clock. And if the gate is greater than 0, then we can check to see whether or not the timer has exceeded the attack time yet. So we'll route the true output of the last router into another compare module, and we'll compare it to our attack time, which is also going to be measured in seconds. Alright, and so if the gate is on and the timer is less than the attack value, then we know that we are still in the attack phase of our envelope, so we can create the attack clock. And if the timer is greater than the attack time, then we know that we are either in the decay or sustain sections of the envelope. So again, we can compare the true signal of the last router to A plus D in this instance. We want to make sure to see if the timer has exceeded the attack time and the decay time. If it hasn't, then we're still in the decay phase. If it has, then we are in the sustain phase, and we can create a quick bus for each. And then we'll create a macro that accepts one of these clock signals and uses it to crossfade between two values that are going to represent the beginning and the end points for that stage of the envelope. So for example, for the attack stage of the envelope, we're going to start at a value of 0, and we're going to rise towards whatever the incoming velocity is from our most recent MIDI gate. And so that macro is going to have 3 inputs. We're going to have the beginning point, the end point, and the crossfade point. So if the crossfade point is equal to 0, then the output will be equal to the beginning, and if it's equal to 1, then the output will be equal to the end, and if it's somewhere in between, it'll be, faded between those values. So, as I said, we're going to use the beginning point is going to be 0 for the attack phase, and the end point is going to be our velocity, which we're going to grab from the incoming gate signal. So we've already checked to see if the gate is greater than 0. And now let's just create another router that receives the gate as its input. And if it's greater than 0, we'll route it to a quick bus called velocity, which we can send to the endpoint of our attack stage macro. And the X value is going to be from our attack clock that we created earlier. But that's going to give us a time in seconds instead of a 0 to 1 value that we want. So we're just going to divide the attack clock over A, the total attack time. So we're going to have whatever time is currently being counted by our timer being divided by the total length of the attack phase, and that'll give us our value between 0 and 1. And as I mentioned earlier, we're going to be using optional clocking here. So we've already created our optional clock, but now we need to make sure that these macros are only going to output values when they receive values from their clocks. So the clock in this case is going to be our X value that we're receiving that's being created by the attack clock. And so we just want our beginning and end values to be stored in a latch until we receive a clock input. And when we do, we can read out those values, and we'll multiply the end value by the X value. So again, if X equals 1, we'll just keep the end value. And we'll multiply the top one by 1 subtract X. So, again, if X equals 0, then we'll be multiplying the beginning value by 1. And then we'll take these two values and add them together. And that's going to be it for this macro, which in many ways is very similar to the crossfade macro in primary, and also the xfade macro in core. However, the xfade macro from core has a few properties that make it not very ideal for this exact implementation, and they don't work very well with optional clocking. And next, let's take a moment to look at the modulation menu inside the expert macro menu. And what all of these modules do is allow you to store one of the parts of the multiplication or division or whatever into a latch, and to only execute the multiplication when a value arrives at the signal input. So there's a signal input and a parameter input, and the parameter input doesn't cause an output at the end. It just gets stored in a latch like we had previously. So we can just replace the latch and multiplication that we have with a single modulation macro. It's not going to be more efficient or anything. It just looks cleaner and it's easier to make. It just makes for faster building. And again, this is optional clocking, and right here we have, with this division, a setup where if the attack value changes, we're going to force the stage macro to create an output, which we might not want. So instead, we're just going to store any incoming attack values in the parameter input of a modulation macro, and that way our stage macro is only going to output a value when it receives a value from the attack clock. Alright, so that covers our attack stage. We can duplicate this whole process to create the decay stage. And we're going to have to change the inputs to the macro a little. We're going to start at the velocity time. And it's tempting to simply travel to whatever the sustain value is here, but that's actually not going to work quite properly. We actually want to multiply the velocity by the sustain value. So for example, if your sustain value is 0.75 and your velocity is 0.5, if you used the sustain as an input here, the decay stage would actually be traveling from 0.5 to 0.75. It would be moving upwards when it's supposed to be moving downwards to 0.75% of the, or 75% of the maximum value of the envelope. And our decay clock is going to have a value from the attack time to the attack time plus the decay time is going to be its maximum value. So we're just going to subtract the attack time from it to remove that from the equation altogether, and then we can divide it by d to get our value from 0 to 1. And that's going to make up our decay phase. Finally, our release phase is slightly more complicated. The beginning is going to be whatever the last output value from our envelope is, so we'll talk about that in a moment. And the end time is going to be 0, as we're traveling from wherever our envelope got released to 0. And for the x input, we can divide the release clock over the release time. And since we don't really have an end for the release clock, it's just going to keep running even when the envelope is off. We just have to make sure this value doesn't get greater than 1. And that's kind of been built into the other clocks implicitly, but we haven't done it with this one. So we just need to clip it at a value of 1. And so that means the output of this macro will never be greater than 1. And we can send it directly into our stage macro. We're going to merge these three values together. And the output of this merge will be the output for our envelope. And we're also going to use it for the input of our release stage beginning. So whenever the gate is released, we want to take whatever the last value from the envelope is and set it as the beginning of our release stage. So we'll just store the output in a z-1 module. This is just going to delay the output by a single sample clock. And we're going to trigger this whenever the gate is turned off, so we can create an off clock right here. So you might be noticing now that we never did anything with the sustain clock at all, And the reason for that is when the decay time is done, we're already at the sustain time, and just by doing nothing, we can stay there. So that's pretty much the easiest way to do it. You can even delete the sustain clock quick bus altogether. Okay, so in order to test our envelope, let's connect it to a MIDI gate and create some arbitrary attack, decay, sustain, and release values. And when I'm done with this, we'll connect the whole thing to an audio table, and I'll make a simple little structure to record the output of the envelope into the table so we can get a look at it. So just run the envelope directly into the in input, and I'm going to use the gate to trigger an integrator filter. Whenever we receive a gate value greater than 0, we're going to restart an integrator filter at 0 using the set input and a value module. And that's going to restart our integrator. And if we declare an input time of the sample rate divided by 1000, then we can use the output of the integrator as the driver for the WX input of the audio table. And we want to make the audio table pretty sizable so we can get a good look at a wide range in time. So I'm just going to create it so it has 441,000 elements, and that'll be 10 seconds of audio. And here's what it looks like. Alright, so this is a very basic ADSR envelope, and in the next tutorial I'll show you how we can spruce it up a bit by adding some curves.